All right, so here's the Unit 7 review. Let's do it together. You know, you need to do it first, right? And then watch the video to see if you did it correctly. So here's the assignment. I'm going to do it on another piece of paper like you should. So you should write down Unit 7 review. Try to be organized. Start with number 1. So you're given the sequence 2 plus 5 over n. And the first question is, does the sequence converge? So we're going to write it as a limit as it approaches infinity. And think, does this converge? So take a moment and think. So 5 over infinity, whenever the bottom is more powerful than the top, this is 0. So it ends up being 2 plus 0, which is 2. So it does converge. B, is the sequence bounded? Now, what does that mean? So let's first of all look at the terms. If I plug in 1, I get 7. If I plug in 2, I get 2 plus 5 over 2. If I plug in 3, I get 2 plus, I'm going to see. I'm not going to start the video over again. I don't care if I see. All right. 3, 2 plus 5 over 3. 2 plus 5 over 4. 2 plus 5 over 5. And then what's happening here as it's going? So eventually it is going to 2. So this answer is eventually going to get to 2. And the largest answer was 7. So this is bounded between 2 and 7. It won't be equal to 2. C. It says, is the sequence monotonic? What does that mean? So is it only increasing or only decreasing? So look at the terms. If you look at 7, then 4.5, and then 2 plus this, 2 plus this, 2 plus this, as it's going all the way to 2, it is monotonic because it's only decreasing. All right, number 2. Write a formula for this sequence. And some of these could be reduced, but there's a good reason not to. So I want you first to think, what pattern do you see? So when I look at the numerators, I see that you're multiplying by 3 every time. Do you see that? So because of that, it's called geometric. So for the top, the geometric, this is what we're looking for, is the first term times the ratio to an exponent. So this ratio is what you're multiplying by. The first term is 2. So we have 2, and then that base. And so if I plug in now, I might put it, would you put n minus 1 there? Whereas if n equals 0 or not. So if n equals 1, then we'd have n minus 1 to that. If n equals 0, then it would just be n. How about the denominator? 2, then 5, then 8, then 11. Can you see it? So this is called an arithmetic sequence. It's linear. And so as you add, that's like your slope, which is 3. And the first number, your a1, is like the y-intercept. So think of this as y equals mx plus b. So the slope is 3, and the y-intercept's 2, and so it would be 3n plus 2. And then test it. Did it actually work? Oh, here, let's make n equals 0, and then it'd be a little bit simpler. So if I plug in 0, 3 to the 0, that works. Plug in 0, that works. And then it's going to increase by 3 on the bottom, increase times 3 on the numerator. All right, there it is. And again, the top was geometric and the bottom was arithmetic. Number 3. Integrating from 0 to infinity what would the answer be? So the question is, what was the question? Give a reason why they're improper. Well, it is improper. Why? Because the upper limit is infinity. How about B? Integrating from 0 to 5, 1 over x squared subtract 25. Why is that improper? And at x equals 5, which is the upper limit, or bound, there is a discontinuity. C. From negative 2 to positive 2. So if I look here, if I plug in any number here, is there any discontinuity? So I'm going to look at the denominator. So I'm going to do that on the side. Just the denominator equal to 0. If I factor out an x, I notice that there are two numbers that x cannot be in the bottom. It can't be 0 and it can't be negative 1. So there are two discontinuities between the limits or bounds at x equals 0 and negative 1. So you have two numbers between negative 2 and 2 that are discontinuous. That makes it improper. Number 4. All right. From 1/2, or is that negative 1/2? Let me just look carefully here. Is that negative? That's negative 1/2, my eyesight. So negative 1/2 to 2, and then 2x plus 1 over x squared plus x. So similar to part C, but the limits are a little different. So how would I set this up? So we said negative 1 and 0, right, for the last one. So negative 1 is no longer in this interval from negative 1/2 to 2. But 0 is. So we're going to set up an integration from negative 1/2 to 0. We'll do this in 2 steps. And then the second one would be from 0 to 2. Then we're going to set these up as limits. So for this one, I'll say the limit as b approaches 0, and then change it to b. And then for the second one, again, as a limit, I was going to call that as a approaches 0, from a to 2 of the same one. All right, take a moment. So when there's a discontinuity, we're going to write it as a limit. As it approaches that number, what's happening? And this is from the left, and this is from the right, in terms of what we're looking for. So one's from the left and one's from the right. All right, now we have to integrate it. So if I look at the denominator, the derivative of the bottom matches the top exactly. This is a logarithm. So we're going to write down the limit as b approaches 0 from the left, and then the answer, which is the logarithm of x squared plus x from negative 1/2 to b. And then the second one, same thing, integrating, right? So again, I got to write the limit notation from the right. Again, it's the logarithm of x squared plus x from a to 2. And now we're going to substitute in and see what happens. So first I'm going to plug in b, top limit first. Again, keep the limit notation. And then I'm going to plug in a half. That's a quarter plus a half. Well, it's a quarter minus a half, I mean. So it ends up in the absolute value of that, so it's 1/4 minus a half, ends up being negative a quarter, but the absolute value, that's going to be a quarter. So the next one, again, I'm going to plug in 2 first. That's 2 squared plus 2, 6. Subtract. Again, I'm going to write this as a limit. And I'm going to plug in a from the right. So the question is, what happens here for this logarithm as it's approaching 0 from the left? So if you think of a logarithm in terms of how it's approaching, so from the left, there isn't even anything there, and even from the right, it's going there. This completely diverges. It does not converge to a number, that logarithm. So we can then say it diverges. Number 5. Evaluate from 1 to infinity 2 over x cubed dx. So we can tell it's improper because of the upper limit. So it's the limit as, I'm going to call this b approaches infinity from 1 to b. I'm going to write it calculus friendly. And then I'm not going to lose the limit notation yet. So then I'm going to integrate this. So I'm going to add 1 to the exponent and divide by that exponent from 1 to b. I'll simplify it. So 2 divided, that's negative. Then I'm going to substitute in. So keep the limit notation. I'm going to plug in b to begin with. Now, x to the negative 2 means 1 over. So this is going to be 1 over b squared minus, now because it's negative, a negative and a negative is going to make it plus, and then when you plug in 1 to anything, it's just 1. And then the question is, does this exist? So when I plug infinity, what's 1 over infinity? Does this converge? The bottom is more powerful than the top. This converges to 0, which leaves me just the answer of 1, and you did it. All right, number 6. So determine if the series converges or diverges and give a reason. So if I write this as a limit going to infinity, this does not equal 0. It goes to infinity. They call this the nth term test. So it diverges. Number 7. And it might be helpful to rewrite this so you can see it better as 5 and 1 over 4 to the n. That means the same thing. Because I think now you would see it does. What's the limit as n goes to infinity? Actually, we don't even need to write a limit. We can just know that the common ratio is less than 1. That's the geometric series test. So because the ratio is less than 1, this converges. We could also write as a limit, and the limit would actually go to 0. 8. So again, I'm going to rewrite this. We know when you divide by a fraction, we can actually rewrite it so that you can see it better. This is really what it is. You know, when you divide by a fraction times the reciprocal. And so here the ratio is greater than 1, which means it must diverge, right? If I can spell that word. And again, by the geometric series test, because the ratio is bigger than 1. Number 9. All right, so this is an alternating series, so two things need to happen. First, is this monotonic? So as I plug in 1 and 2 and 3, notice the bottom is more powerful. So as you plug in numbers, it's going to decrease, decrease, decrease. So first of all, this is decreasing. And second, the limit, as that goes to infinity, equals 0. So it's decreasing, it's going to 0, therefore it converges, and this is called the alternating series test. Number 10. I should remind you, you should try it first. Show for 4 terms and a general term of the geometric power series. All right, so step 1 is to find the ratio by putting it in this form, 1 subtract. So for this to work, it needs to be 1 subtract. So the common ratio is negative 3x. The first term is the numerator. So the first series would be x and then multiplied by negative 3x. So that'd be negative 3x squared multiplied by negative 3x. That's positive 9x to the 4th. Multiply again, negative 27x to the 6th. Right? Oh, sorry. These are, exponents went up too high. So if I go negative 3x times negative 3x squared, it's x cubed. If I go negative 3x times 9, it's negative 27x to the 4th. I was just being too aggressive with the exponents, but everything else is good. All right, and then find the interval of convergence. So the common ratio, negative 3x, must be between what two numbers? And then divide by negative 3. And when you divide by a negative number, it just flips. So the negative 1/3 is on the left and the positive 1/3 is on the right. And this is called the interval of convergence. Number 11. You're given a series 3 plus 6x squared plus 12x to the 4th, 3, 2x squared to the n. So it says write a function for g at x. So the first term, because you're multiplying every time by the same thing. So a1 is 3. Your common ratio, what are you multiplying each time, is 2x squared. So the formula is a1 over 1 minus r. And that, of course, if the interval of convergence, that common ratio, divide by 2, and square root. Interesting, right? Or did it already say? All right. I'm not going to worry about this part then. Square root of a negative number. All right, number 12. Show 4 terms of the derivative of x. So the derivative of 3 is 0. The derivative of 6x squared is 12x. So I'm not going to put 0 first. Is 12x. Next one is 48x to the third. I need the next one and the next one to do the first 4 terms. So the next one, keep multiplying by 2x squared, and you get 24x, and you get, again, 48. So 6 times 24. And then 8 times 48. And that is the derivative for the first 4 terms. Number 13. Show 4 terms in a general term of integrating this from 0 to, I think that's a t. Let me make sure. I do this to like zoom in. It is a t. Look at that. It looks like a 1. T. So I need to integrate each one. So this is going to integrate and then plug in t. So it's going to be 3t. The next one I'm going to add 1 to the exponent and divide. The next one I'm going to add 1 to the exponent and divide. And then the next one, I'm going to add 1 to the exponent and divide, which is 24. So 7 divided by 7. All right, number 14. Show 4 terms of x squared g at x. So you take each term and just multiply it by x squared. So that's going to be 3x squared, 6x to the 4th, 12x to the 6th. Remember the next one was what, 24? 24x to the 8th. Number 15. Show 4 terms of a Taylor series centered at c equals 1 for this function. Now I'm going to write it in calculus friendly right away. So what do I need to do? Well, I need to take the derivative, and it says 4 terms. So this is going to give me not a 4th degree, but 4 terms. So 1, 2, 3, 4 terms. So this is negative 1/4 x to the, subtract. All right, multiply, that's positive 5 over 16, x, and then subtract 1, negative 9 over 4. Multiply again, I get negative 45 over 64, and subtract. All right, those coefficients are important. So when I plug in 1, this is what I need, 1 to any exponent. If I plug in 1 here, 1 to any exponent, but I'm left with negative 1/4. All these coefficients is what I'm left with. So 5 over 16 and negative 45 over 64. So 1 over the 4th root x is equal to approximately, what's the pattern again? So it's 1 minus, it's 1/4. Now it's centered at 1, so it's not x, but x minus 1 to the 1 over 1 factorial. The next one is 5 over 16, x minus 1 to the 2 over 2 factorial. And the next one is minus 45 over 64, x minus 1 to the 3 over 3 factorial. And there is 4 terms, and it's done. 16 says, use the second degree Taylor polynomial, so that's right here, second, x1 and 2, to approximate 1 over the 4th root of 1.1. So what that's saying is x, in this case, is going to equal 1.1. So wherever there's an x, you plug in 1.1. And again, it's a second degree, so I end there. And then you'd plug that into your calculator. I'll save you the pain. And then that answer is what you would get. Number 17, use an elementary series to write a power series for y equals e to the negative x. So e to the x is 1 plus x squared over 2 factorial, x cubed over 3 factorial, and so on. That would mean this would be then 1 plus negative x, use parentheses, plus negative x over 2 plus negative x 3 over, and then so on and so forth. And then number 18, it says use 3 terms of an elementary series to approximate sine 0.2. So to do that, we start with sine x and go, okay, what does it start with? It alternates. It's odd. How many terms? 3 terms. So there's 3 terms right there. And then it alternates. Now what number goes in for x is 0.2. So it would be 0.2, and then it's 0.2 to the 3 over 3 factorial, plus 0.2 to the 5 over 5 factorial. And then you would type that in your calculator. I will do it for you. And it's 0.1988669. Beautiful. Hey, I'm proud of you. You did your work. I hope you tried it first or learned something as you're doing it with me. All right, Mr. G Math. Till next time.